Good afternoon, ladies and gentlemen. Welcome to Physics 30, Magnetism, Lesson 4, Applications of Particle Deflection. Now, a few things here. You need to recall, current makes a magnetic field. Moving a charge in a magnetic field experiences, moving charge in a magnetic field experiences a force. Force magnetic is QVB. And yes, once again, I forgot the vector arrows. And it's velocity perpendicular to the magnetic field. And the direction of force is the third left-hand rule. And right now, everybody should be remembering giving me the finger the one time they can do it. Yes, the same to you. No, the proper left-hand rule. Thank you. Now, applications. First one, the aurora borealis or northern lights, and aurora australis or southern lights. You've got the sun, solar wind, and earth. Now, the surface of the sun is about 5,000 degrees Celsius, produces plasma, hot charged particles, hydrogen ions, helium ions, electrons, and so on, released by magnetic solar flares called the solar wind. This solar wind spreads out in all directions, and when it gets to the Earth, the solar wind is deflected by Earth's magnetic field. Remember, these are charged particles. When they hit a magnetic field, like the Earth's magnetic field, they change direction. Now, most particles are drawn to the poles, the North Pole and the South Pole, hence the aurora borealis, northern lights, and aurora australis, southern lights. Now, when these high-energy ions hit the air molecules are excited and emit light. And yes, later on in EMR, we'll explore this in more detail, but oxygen tends to glow red and green. Nitrogen is blue and violet. So you see the northern lights, they tend to be lots of reds and greens, but you also see blues in there. So that's mostly oxygen, thankfully. If we didn't have oxygen, we'd all be dead now. So, All right. Malachi, do you have a copy of these notes? No, you don't. All right. Wait. I'll give you a copy. All right. Now, you're not using this. Oh, never mind. Now, no charged particles move in a magnetic field have a force magnetic QVB. Now, this question is popular in the diploma because you've got centripetal motion from Physics 20, mv squared over r. And you look at your formula sheet, that formula's not there. Something they expect you to know. So the force magnetic, Fm, I'm sorry, not Fb, equals force centripetal, or QVB equals mv squared over r. So here's a lovely equation we get to play with. Now, how can we play with that? Can of gasoline, some matches? Not that kind of playing. How would we play with that? Yes, we have everything except for one, and then we have to find the rest. Now I'm just, sorry. Oh, yes. I want to point out here, we have velocity on both sides, so v and v. So quite often this is qb equals mv over r. So, and generally I'll give you 4 of them and we'll figure out 5. All right, so far so good? Now, later on in class, we will talk a lot about charge to mass, Q over m. You rearrange this equation, Q over m equals V over BR. All right, so that's a popular way to rewrite this equation. So far, so good? Yes, silence, no silence? Just sitting there staring at me. Okay. Now, if an electron is moving at 2.38 times 10 to the 3 meters a second into a perpendicular 1.13 Tesla magnetic field, what's its radius? So, it's going to go into magnetic field. Now, I didn't say which way it's going, direction of the magnetic field. I didn't give you a picture for that. But I want you to realize force magnetic, force centripetal. QVB equals mv squared over r. This is the way I do it. I remember force magnetic is QVB and force centripetal is mv squared over r. And then I go, oh, I can cancel out one of my v's. So QB equals mv over r. So I'm looking for radius here. Nice one. So my first thought is I'm going to rearrange this to solve for R. R equals mv over qb. Now, do I have to show you how I got that? Multiply both sides by R and divide both sides by qb. Okay, good. It's physics 30, not math 10. All right, so that's my formula I'm solving for. R equals mv over qb. Now, going back up to the question, electron. So do I have the mass of an electron? Well, I don't have it with me. Where is it? In your formula sheet that you should have out right now. Did not come to physics. Where is it? God help me. Come to physics 30 class without your formula sheet. You're lucky I'm scared of you, otherwise I'd be making an example. All right, that's for the rest of you. Where is it? Good man. You're supposed to have it out, unless you happen to have this mass memorized. So, radius, 9.11 times 10 to the minus 31 kilograms. The velocity. What was the velocity? 8 times 10 to the 3 meters a second. Charge on electron. And the magnetic field strength in the question was 1.13 Tesla. So plugging those numbers in. Actually, I'm going to color code this. And somebody didn't bring a calculator. God help me. All right. So can you put this into your calculator properly? I hope so. Yes, we're about to find out and about to get sarcastic with the two people who can't bring freaking cheesy calculators. Anyway, moving on. Nothing. Yes, I'm looking for an answer. Hang on. Now, one student just said 1.53 times 10 to the 8 meters. So let's do some estimation. I know. 9 times 10 to the minus 31. 9 times 2 is 18. So minus 31 times 3 is minus 28. Minus 28. Okay, that sounds better. 1.19 times 10 to the? All right. Now, students in class are giving me different answers. I suspect it's because they didn't put this in brackets. So, do I have to pull out Mr. Calculator and show it to you? Okay. Physics 30, do not use a no comment. No comment. No. You're the sweet, kind, quiet one. 9.11 exponent negative 31 times what's its velocity? Exponent to the 3. Okay. Divided by 1.6 exponent to the negative 19 is divided by 1.13 Tesla. 1.1992 times 10 to the minus 8. That I believe. That would be 1.20 times 10 to the minus 8 of a meter. Shh. Okay, so that's the radius of a charged particle in a magnetic field. See how that goes? All right, now, you guys still suck at these, so we practice more. If the same electron is moving at half its original speed into a perpendicular magnetic field 3 times stronger than part A, what's its new radius? Now, what is this? A ratio and proportion question. Now, can you plug in the original numbers and solve? Yes. Can you do it as a ratio and proportion? Yes. Yes, you can. Well, you're supposed to be able to, because, sorry. Would you stop doing that while I'm recording this tape? And I'll deal with him later. All right. So, what we say R is, what the heck did I say it was? MV over QB. No, do not memorize this version of the formula. Be able to derive it. So the new radius, half its original speed, m 1/2 v, and 3 charge doesn't change, but the magnetic field is now 3 times stronger. What do we get? 1/6. 1/2 divided by 3 is 1/6. Or 1/6, whatever original radius is. Now, most often on the diploma style questions, I'd say the original radius is R. In this instance, we happen to know what the original radius is. We can divide it by 6. Are we going to spend class time doing that? I hope not. Just either take your original answer divided by 6, please. Now, so far so good? All right, now. All right, now I'm currently handing out this applications part of deflection, the mass spectrometer. Everybody have a copy? Take one, pass the rest back. Yeah, some of you guys are getting blue handouts, some of you are getting white because Mr. Photocopier decided to be a poo head again. Anyway, now, some notes for you guys to fill in as we go along rather than the standard smartboard. Anyway, so these are notes. No, I don't want to see them again. Put your name on them so if you leave them behind, I know who to yell at. All right, Physics 30, Forces and Fields, Application of Particle Deflection, the mass spectrometer. J.J. Thomson, 8 of spades, used electric and magnetic fields to determine the charge to mass Q to M ratio of electrons. Now, why is this charge to mass ratio important? Well, we just derived the formula I warned you about. Okay, don't be like that. Q over M equals what? We just did it in our notes. Okay. Now, just stop it now. Okay. Now, here's something I want you to note. Can we measure the velocity of stuff easily? Yes. Can we measure the magnetic field? Yeah, well, if we're making it, yeah. Can we measure the radius of something moving in a magnetic field? Yes. Is it really easy to measure the mass of like electrons and protons? Is it really easy to measure the charge in electrons and protons? No. Okay, so what he was doing here is charge and mass is hard to measure. But velocity, magnetic field, and radius is easy. Now, the reason it's so hard is, well, one of the reasons is we have 2 unknowns, charge and mass. So we need a second equation. There's no way to solve one unknown or one equation with 2 unknowns. Right. So, in later experiments, he made similar measurements for positive ions. These experiments led to the development of the mass spectrometer, an instrument that can detect compounds, measure isotope masses, and determine molecular structures. But there we're getting into chemistry stuff, and I don't want to talk about it because it's chemistry. So, mass spectrometer consists of 5 parts, or 5 major parts. So here, ionization chamber, or ionization source, acceleration plates, velocity selector, deflector array or deflection chamber, and the last part, the detector. That's not considered important here. That's like on the cathode ray tube. It's there. If it's not there, it doesn't work. Like electricity. Okay. So far, so good? Okay. Now, first things first, the ionization chamber or ionization source. If the sample is not already a gas, the ion source vaporizes it usually by heating. Now, heating may also break complex compounds into smaller fragments that are easier to identify. Usually, one or more of the electrons are removed to produce an ion. Now, why is it necessary for an ion, not an atom, to be used? Yes. Well, guys were saying ion has a charge. Charged particles are accelerated by magnetic force. No charge, no force. Good. I mean, good. Well done. Should say charged particles accelerate. Magnetic force. Okay, now, the next part, acceleration plates. Now, the ions move through a set of parallel plates with potential differences between them. There's a hole in the plates for ions to pass through, and the ions are sped up to move into the velocity selector. So, here, positive charge, it's accelerated too. So, an acceleration plate has a potential difference of 500 volts. If the particles to be accelerated are copper 2 plus ions, mass 9.48 times 10 to the minus 22 kilograms, and they're starting from rest, what's their final speed? Now, this goes back, I just talked about voltage. Where have we seen voltage before? Sorry? Oh, change in voltage is change in energy over charge. And remember, that's energy kinetic. So that means change in energy, change in voltage times charge, and change in energy kinetic. Yes, so 1/2 mv squared equals change in voltage times charge. So can we figure out the final velocity, considering initial velocity 0? Yeah. And somebody would point out, but Mr. Sutton, shouldn't this be change in velocity? Yeah, it should be. I just forgot to write it out. Anyway, so we know mass of an electron. Well, we don't know it. We can look it up. Do we know the voltage? Yes. Do we know the charge of an electron? We can look it up. Yes. I suppose. Language. All right. Be quiet. Teenage boys, God help us all. You guys be quiet now. I don't want this on. I have enough problems with my tapes on YouTube. All right. So voltage times charge times 2 divided by mass will give us V squared. One of you youngins with a calculator, tell me what the answer is here. What's V squared? 500 volts times 1.6 times 10 to the minus 19 of a coulomb times 2. Mass is 9.11 times 10 to the minus 31 of a kilogram. Oh, sorry. That's mass of electron. What am I smoking? Never mind. Oh, thank you. And sorry, I'm thinking electrons. Hang on, guys. Note here, it's charge 2 plus, so this is 2 times 1.6 times 10 to the minus 19 coulombs. Thank you. Good catch, guys. And mass is 9.48 times 10 to the minus 22 kilograms. Helps to actually answer the question I'm asking, rather than the question I'm thinking about. Never mind. 500 times 2 times 1.6 times 10 to the minus 19 times 2 divided by 9.48 times 10 to the minus 22 is? Come on. Okay, I'm having two people blurt out answers. Can one person say it clearly, loudly enough I can hear it? What you get? Now is that? Did you square root it? No. Now that's a reasonable velocity for ions in an accelerator, 580 meters a second. Yeah, like I did. Ugh. Okay. I'm just going to nod and agree with him too. All right. Okay. Now, next thing, the velocity selector, my personal favorite. Particles enter into an area of perpendicular magnetic and electric fields. These fields are set so that particles do not deflect. If this happens, we can calculate the particle's velocity. Ions with slower or faster speeds are deflected away from the entrance to the detection chamber. Thus, all the ions entering the next stage of the mass spectrometer have the same known speed. So what is the velocity of an alpha particle if the electric field strength is 500 newtons per coulomb and the magnetic field strength, is 0.75 Tesla? Now, look carefully at the picture here. What have you got? You have two parallel plates. What's the direction of the electric field? Yes, the electric field is going up. Look at the picture here, positive to negative. What's the direction of the magnetic field? Grab your left hand. The magnetic field is coming out. Thank you. So, yes. Right hand, thank you very much. Positive charge here, not negative. God help me. So we go to the right hand, and everybody's giving the finger to the door. All right, so the magnetic field is going which way? Circles means out. Direction of the object is to the right. The force is, magnetic force is? Down. So magnetic force is down. Who wasn't here yesterday? Okay. All right. So very quick, sorry, somebody missed yesterday. Third left-hand rule for direction of a charged object in a magnetic field. Give me the finger. Left hand. All right. Yes, the first one of the few times you can do it without getting it bitten off. Now. Yes. Left hand. No. Left. Give me the finger. The middle finger is the direction of the magnetic field. Okay? Now when you make the pistol like this, the index finger is the direction of the current, the bullets, and the thumb is the recoil. So this shows you the force. Sorry, the thumb. Really good people watching the video, listen to me. Thumb shows direction of force. The index finger shows direction of the charged particles, and the finger shows the magnetic field. So here the magnetic field's coming out. Now this is for negative charge. So if this is a negative charge, it'll be going up. We do the opposite for positive charge. We twist around, and then we go the force is down. So if this is going through, well, you shazbot, stop that. Yes. You should see some of the comments I get. Now, F sub M equals F sub E. Now, question? No, no, index finger's direction of the charged particle's movement. Thumb is the recoil of the force. Bang. Bang. Yes. And what is your issue besides being micro-squish? Now, you can see why they like this, because there's a lot of stuff from the previous chapter, plus we're getting into circle again. Now, what's the formula for force magnetic? B. Anybody remember force electric? That's force. No, that's for two charges. EQ. Now, QVB equals EQ. Can we simplify this mess? Yes, we have a charge on each side. So this becomes velocity times magnetic field. Make that a little nicer. Equals the electric field strength, or velocity equals the electric field strength divided by the magnetic field strength. So you can calculate the velocity. Or, so you can calculate the velocity if you know the electric field and the magnetic field. Since you're creating both of them, that's easy enough to measure. Now, I did ask here, oh yeah, what is the velocity? What's the electric field? 500 newtons per coulomb. And the magnetic field is? 75 Tesla. So what's the velocity we got spitting out here? I think about 667 meters a second. 0.6, which runs off to 667. That's what I got. Now, I'm happy I didn't hear that comment. Be quiet. All right, so this is how velocity selector works. Notice, once again, nothing particularly difficult, but lots of formulas. Got to pay attention. And God help me, it's so easy to screw up. So I'm giving you these notes to hold on to. Now, the next thing is a deflector array or deflecting chamber. Now, I want to stress this here. Particles enter the second different uniform magnetic field. So there's two magnetic fields here. There's the first one in the velocity selector, and then there is the second one in the detection chamber. So if you're not careful and read the question not carefully or quickly, you might miss one of the magnetic fields. And guess what? One of the distractor answers in the multiple choice will take that into account. So when the particle enters the second different uniform magnetic field, the deflector travels in a circular pattern with a radius r. Given this radius, the velocity in the magnetic field, the charge to mass ratio of the particle can be determined. Now, I want you guys to determine the charge to mass ratio of the alpha particle using data from the previous example, given the particle deflects with a radius of 1.26 times 10 to the minus 5 of a meter. 1.26 times 10 to the minus 5 of a meter. Okay? Okay. So what's the first thing you have to do? Yes, someone can read. Good. Force centripetal equals force magnetic. Centripetal, what's the formula for centripetal force? mv squared over r equals qvb. Now, solving for q divided by m. Well, notice one of the velocities cancels out. We divide both sides by mass. And charge, and then we have to divide both sides by b to get that b to cancel out. So charge over mass equals v over br. So yes, now careful. What B are we talking about? This magnetic field or the second magnetic field in the deflector. Now, we just calculated the velocity of the alpha particle going in. What was it? 667 meters per second. What is the magnetic field of the detection chamber? Tesla, yes. Right up here, 1.10 Tesla. Not the 0.75 of the velocity selector. And what did I say the radius was? So, what's a charge to mass? What is our charge to mass ratio of this? Yes. Somebody tell me. And that is coulombs per kilogram. Yes. That's what I got. So, some big numbers there. Now, what does that number mean to the mass of a particular ion? Now, as I said, this is before they found out the elementary charge or the masses of these atoms or ions. So this is very difficult. Okay, now, the detector collector, ions arriving at the detector produce an electrical current that's proportional to the number of ions. The spectrometer can produce a graph of the charge to mass ratios for a sample by moving the detector or by varying the electric or magnetic fields. Now, as I said before, at this time they don't know the elementary charge and they don't know the masses of these individual ions, so they're stuck with the charge to mass ratio. But particles have a distinct charge to mass ratio, like a fingerprint. By determining the charge to mass ratio, the particle can be identified. Now, what particle did we just run through the mass spec here? Alpha. So we just ran through an alpha particle for 2 helium plus 2. What's its charge to mass ratio? We did 4.81 times 10 to the 7. Okay, this. Hang it. Back up. Back up. Said so. So alpha. I can't spell alpha very well, so we'll use this abbreviation. It looks like an infinity symbol with a bite out of it. That's the Greek letter A. Now, depending on the font, it might look a lot more like that. Most of a fish. Yes. Well, what is an alpha particle? It's a helium atom that's lost its 2 electrons. Well, that's what I'm telling you. Okay, if you look at a helium atom, it has 2 protons. A standard helium has 2 protons and 2 neutrons in the nucleus. So a total of 4 elementary particles in the nucleus. 2 of them are protons. Correct. It's telling you the 2 tells you 2 protons, and the 4 tells you you're dealing with 4 particles in the nucleus, because you can't get helium with 3 particles in the nucleus, 1 neutron, 2 protons. That's particularly good if you've had a nuclear war. You'll see lots of that, unfortunately. And you'll get some of that 5 too, but that's not very stable either. All right, now, can you tell me the charge to mass ratio of a copper 2 plus ion? Well, I've told you the mass. What's the charge on the copper 2 plus 2? 2, yes. So, Q over M, 2 times 1.6 times 10 to the minus 19 of a coulomb, divided by 9.48 times 10 to the minus 22 of a kilogram. So what are we getting for this? Don't make me scream faster, faster, you fool on tape. What are you getting? Sorry, coulomb per kilogram. Now note that's very different than the 4.8 times 10 to the 7. All right? So, it was fairly easy for the early scientists to calculate the charge to mass ratio. They just didn't know the charge or the mass. So they left it as charge to mass ratio. Now that we've with Millikan's oil drop experiment, this is easy to solve, but I'm saving that for later. I'm bringing this up because you will see the odd charge to mass question on a diploma. Hint, hint. Any questions so far? All right. Okay. Well, you can always ask. So, 3 quick questions before I give you your homework. No, this is practice. Make certain you guys understand it. Woo-hoo. All right, I don't even want to know what you're talking about. A doubly ionized atom, charge that has Q of 2 electrons with a mass of 6.8 times 10 to the minus 27 kilograms, enters a 3 Tesla magnetic field with a speed of 5 times 10 to the 7 meters a second. What's the radius of the circular path of the atom? Typical diploma question. What do I expect you to do? F sub C equals F sub M, mv squared over r equals qvb. Cancel out one of these. mv over r equals qb. So here we are looking for the radius, so it's rearranging the equation. Radius is mv over qb. Can we solve that? You know the mass. Yes, did I give you the velocity? Did I give you the charge? Did I give you the magnetic field? Yes, so solve it for me. Ratio. 6.8 times 10 to the minus 27 kilograms. 5.0 times 10 to the 7 meters per second. 2 times 1.6 times 10 to the minus 19 of a coulomb. Okay. And 3.0 Tesla. What'd you get? 0.35 meters? Well, what did you get exactly? 0. Okay. Should we believe him or throw things at him? Yeah, I gotta be careful. So, typical diploma question. I actually took it off a diploma. Now that you... What is your issue besides being microsquish? God help me. There we go. Okay, sorry. Okay, somebody not get that answer? Okay, did you bother putting brackets around your denominator? Or you just divided by 2 and then multiplied by everything else? That would explain a lot. Good plan. Okay. So a charged particle travels in a circular path of radius r while in a uniform magnetic field. Which charge doubles the radius r? Well, we just did it in the last question. R is what? V QB. So how can we double R? Louder? Now somebody's blurted, I apologize to those listening to tape, somebody just blurted out an answer, but I couldn't make it out. Was it B as in Bub or D as in Delta? Why'd you say D as in Delta? Because it works. Yes. R is mv over q1 half b. Yes. Yeah, you're doubling the radius. Yep. Twice the charge will cut it in half. Doesn't work. Half the mass and twice the speed will double the radius. So hang on. Twice the speed. Half the mass and twice the speed will cancel out. Half the speed and half the mass will give you 1/4. Yes. Now I just said that orally without proving it. So I'm randomly going to, I'll prove A to you. Does not work. So if I go half the speed, so that's 1/2 v, and half the mass, 1/2, that becomes 1/4 the original radius. So that doesn't work. All right. And you guys prove the other 2 to yourself. Now, number 3. Proton is traveling in a circular path of radius 0.19 meters perpendicular to a 0.55 Tesla magnetic field. What is the momentum of this photon? No, what is the momentum? Back up. What? Hang on. What is momentum? Okay. Force centripetal, force magnetic. mv squared over r equals qvb. Cancel out the v's. We got mv over r equals qb. What's the definition of momentum? Mass times velocity. Do we have mv in the formula? Yes. Can we isolate it? Yes. mv equals qbr. By chance of the charge. What's a proton? Yes. Do we know the magnetic field? Yes. Do we know the radius? So I don't have to give you the velocity to figure out momentum. Almost like I planned it that way. Yeah, almost. Like I thought ahead, maybe gave you a good question. Never mind. Really, this microphone is picking some of that up. Be quiet. No. Is that because I'm one of the few people on this planet that actually listen to these tapes occasionally? All right. Yeah. Anyway, getting back to... I have no idea. Somebody calculate the answer for me. What is it? 1 point what? 1 point... What comes after the 7? 1.67. That, I believe. Minus 20. Yep. All right. So that's how that goes. Any questions? Goodly. So now I'm going to give you your homework, and you can work on that.